You guys up here? Yes, sir.
I know what's happening.
Okay, talk to me about what's happening.
Okay. Oh, I thought this was the second one.
Okay.
This is not as exciting.
But do you still know what's happening,
Yeah.
even though it's not very exciting? Okay.
Yeah.
What's happening?
So the rest, it's going to be 6 all through.
Yeah, they're all going to be 6s. Okay, so these are all going out by 6. Okay, so you're right. That's not as exciting, maybe, as what's happening in number 2. So talk to me about number 2.
So since all of them are 6, it'll be multiplied by 6.
Okay. Because the first difference is constant in the pattern by the algebraic expression. Yeah, okay, so I see what you're saying. So you're saying since they're all going up by 6, then to get these numbers you have to multiply all of those by 6. Okay, good. You see what he's saying? Okay, unfortunately, 6 times 1 is 6, not 4. 6 times 2 is 12, not 10. So how do we make up for that? Yes?
Subtract 2.
Subtract 2. Okay, good. So this is a really important thing for you to understand because it makes finding the formulas for tables a lot easier. If it's going up by the same number every single time, then you know that it's going to start with 6 times n. Okay? And then you just have to make an adjustment. All right? So the way I always do it in my head is I go, okay, I just pick one of them, multiply it by 6. For this one, that would give me 18, which is 2 too big, so I can subtract 2. Okay? There's another way that you can find this number. Does anybody have a different way to think about where that comes from? What would be the 0th figure?
9.
If instead of going up by 6 as we go to the right, if I go down by 6 as I go to the left, what would this number be right here? Negative 2. Okay? And so that's another way that you can do it is you can go backwards and find what the number is that goes with 0, and then that'll be the thing that gets tacked onto here. Okay? All right, questions about that? Pretty easy one because that is linear. All of the ones are the same. All right. How about number 3? Who's got that one? What's the next? What's the difference from 40 to 54? 54 minus 40 is 14. And then the next one is 16, and then 18, 20, and 22. Okay, so now the first differences are not all the same. But what are the second differences? They're all 2. Okay, and so what they want you to understand for this one is that if the second differences are all the same, then instead of being linear, now it's going to be quadratic. It's going to be something square, okay? And that makes things considerably more difficult as far as finding a formula for this. I will do this one with you, and if you go, then don't even worry about it, okay? It's just like if you can get something out of this, then woohoo, but if you can't, no big deal, okay? So since we know the second differences are the same, we know that it's going to be a quadratic equation. So it's going to look something like y equals ax squared plus bx plus c, okay? Because this is what a quadratic one looks like. So our goal that we have to figure out is what are a, b, and c, all right? And the way that we can do that is I can take and plug in 1 in here for all the x's. If I do that, what do I get? Because I'm plugging in for the x's, so what's 1 squared? 1. And then 1 times a is a. So this first term will come out to be a, plus, what's 1 times b? B, plus, so this one doesn't have an x in it, so it's just going to stay as c. And what this table up here is telling me is if I plug in 1 for the x's, what answer should I get? 4. Right? Okay? Then I'm going to play it again. This time with a 2. So if I put a 2 in here for x, what do I get? 4a, because 2 squared is 4, so this is going to be 4a plus, if I put a 2 in here, I get 2b, plus, that's always just going to be c because there's no variable, and this time that equals 10. Okay, now unfortunately, since I'm trying to figure out what a and b and c are, 2 equations isn't going to do it, so I got to go 1 more time. So now I'm going to plug in a 3, and what do I get? You should be able to kind of see a pattern here with these things. 9a, because 3 squared is 9. 3b plus still plain old c, and that equals what? 18. Okay. All right. So then we would like solve that. Okay. But we're not going to mess around with that right now. That's way, way, way too much because there's 3 equations and 3 variables and all that kind of stuff. Okay. So we're not going to worry about that. But you kind of see the idea that the first difference, that means it's linear. The second difference, that's going to mean it's quadratic. If the third differences are all the same, then it is crickets. Starts with Q and ends with Bic.
Quadratic. Oh, no.
Cubic.
Cubic.
Yeah. Bic. I'm trying to make that really easy for you guys. I don't know. Okay. Anyway, so this would come out, you would have to work through that to figure out what that is, all right? And then for these, they would like you to go through and figure out all the equations. What is this going up by each time? 5. So that's easy. It's going to be linear. So I can start out with 5n. Then what? Plus or minus or? Minus 8. And how did you get that?
Because if it was, for the first one, if it was 5n, it'd be 5. And then
Okay.
it's negative 3.
Okay, so he did the method of plug in 1 into here and you get 5, but I wanted negative 3, so to get that I have to subtract 8. You can also walk backwards. If you go back 5, you get to negative 8, so that's where that comes from also. Okay, and then this one would be going up by a different amount, so we're not even going to mess with that. So I just kind of wanted to let you guys sort of see how that pattern goes. Make sense? Okay, I will collect those from you later. Let's start in on section 1 and 2. This is going to go again on a piece of paper that you will turn in later with your homework assignment on. Okay. So this is in your book as well if you prefer to look at that. But in your table group, please answer this question. And I will tell you for today's, there are lots of correct answers. Okay. So the question says, here are 6 emojis. How can you describe a set that includes 5 of the emojis, but not the 6th one? Okay, so we want, I think you can decide which one you want to eliminate. So you can say, I'm going to describe these 5 in a way that this one won't fit, or I'm going to describe these 5 in a way that this one won't fit. It doesn't really matter, okay? So see how many different ways you can come up with a description of those smiley face things that would include 5 of them, but not a 6th one, okay? Go. Okay, let's start by hearing from number 1. Okay, what you got?
The third one in the left. Yeah. Is the only one with its tongue out.
Okay, so you could say emojis that do not have their tongue out. So then that would include 5 of them and not the one. Okay? Somebody else who's a number 1, but you have to oh, you're number 1. I'm just so confused because why did you number things that way? Okay, what do you got?
That smiley face on the left,
Okay.
it doesn't have an outline around its mouth. It's a black outline.
Oh, I see. Yeah, so these have black mouths, outlines, and that one's not. Okay, perfect. So that's 5 out of 6. Cameron?
5 of them don't have glasses.
Okay, 5 of them don't have glasses. 1 of them do. Kyle, did he steal yours?
Yeah,
Do you have another one?
Not really.
No, shot down. Okay, yes.
Okay, 5 of them have both eyes open.
5 of them have both eyes open and 1 of them has at least 1 eye closed. Okay, good. Do you have a different one? That's all we got? Okay. Anybody who has one that we haven't heard yet? Yes.
One is sad and the other is looking.
Oh, what is sad? And the other ones are not. So there's 5. They'll kind of happy. We'll go happy emojis and then one sad one. Yeah. Right. Okay. Okay. Yes.
All of them but one have a crescent mouth.
Ooh, all of them but one have a crescent-shaped mouth. So this little curved thing like that you're talking about. Okay. All right. Good. Good. Okay. Good. Any other ones? All right, good deal. So we've got it. And so what we're going to do is we're talking about being able to describe groups of things in different ways. And of course, the group of things that we're mostly going to be describing in this class would be what? Numbers. Yeah, okay. So we're just going to do a quick little review of all of the different types of numbers that there are. Okay? So let's see what we got here. So this is the big picture right here. And I don't know if there's a better diagram to copy down than that. That kind of looks like that's what we got. Okay? All right, so this is what we got. All of the numbers that we're going to be working with, at least for a little while, are real numbers. Now you might reasonably ask, what kind of a number is not a real number? Does anyone know? Has anybody heard of those? Destiny, do you know?
Huh?
Do you know some non-real numbers? Yeah, I'm hearing it over here.
Irrational number.
An irrational number is a real number. So this real number thing goes around, goes around all of these things right here. Okay? So all of these numbers are real numbers. What's that somebody was saying over here? Imaginary numbers, right. So there are imaginary numbers, and that seems very strange. We will study those a little bit in this class, but not until later down the road. So for right now, any of the problems we do, we're only dealing with real numbers, okay? So all of them are real numbers. Now we're going to split them up into 2 different groups, okay? Irrational numbers and rational numbers, okay? The technical definition of a rational number is any number that can be written as a fraction, okay? So -1/2 is a rational number, 2/3, 5/6. How would I write 0.222 as a fraction? 0.222, or you would go 222 over 1,000. Yes. Okay, so that is a rational number. Okay. 6.1, same thing. You can make that 61/10. So you can turn all of those into fractions. Okay. I'm recording here, so I have to be careful. I don't want my wife to get a hold of this, but the way that I think about rational and irrational numbers is sometimes when you are having an argument with someone of the opposite gender, and I'm looking at you guys, you say to that person, you are behaving irrationally right now. And to me, that means that they're just talking crazy. They're just going on and on and on and on and on, okay? So another way that you can think of irrational numbers is that they just keep going, okay? Now, you can have rational numbers that also keep going, but those would be ones that repeat. So for example, 0.3 repeating is a rational number. Do you know what fraction that is?
1/3.
1/3, yeah. So the reason why that comes out to be a rational number is because we can express it as a fraction. But the square root of 2, if you put that on your calculator, you're going to get just as many decimals as will fill up the screen, and there's no rhyme or reason to how the decimals are coming out, which is how I feel sometimes when I am talking to women. Okay, so all of these are rational numbers because they can all be written as fractions. Then we're going to narrow that a little bit. There's also ones that are called integers, and you can see from up here what is true about integers. They don't have decimals, so they're all whole numbers, okay? But then we have whole numbers right here. So what's different between integers and whole numbers? Yes?
They have their opposites.
Right, integers allow the opposites, the negatives in there, okay? And then if we get more restricted, we've got whole numbers, and then we don't really talk about natural numbers very much, but natural numbers are the whole numbers, but we just left out 0, okay? So does that kind of make sense? So if you are a whole number, you are for 100% sure also an integer and a rational number and a real number, but you may not be necessarily a natural number, Okay, so you can go out bigger, but you can't get into smaller ones, okay? All right, so let's say your school is sponsoring a charity race. That's very nice of us. Which set of numbers best describes the number of people P who will participate in the race? So what is the most restricted, the smallest group that you know will belong to, Seth? Natural numbers, yeah, because I guess you could say whole numbers, like if no one shows up, you have to get a really bad fundraiser, but hopefully at least one person will come, and so the number of people that are going to show up are going to be natural numbers. And now don't say that thing, or if somebody shows up and they don't have an arm, and they're like 3/4 of a person, they're still a full, it still counts as a full person, okay? That is still a full person. So those would be natural numbers. All right, real quick, we don't have to spend more than about 30 seconds on this one, but this is a got it, so this is for you. So just turn to your elbow partner, it's the person that you're sitting right next to, and tell them what you think the answer to this is. $15.50, which set does that best go with? So just tell the person next to you. Okay, what do we go with? Rational. Most of you guys went rational numbers because it has a decimal in it, so it can't be whole number, can't be integer, can't be natural number, so it's going to be a rational number. Okay, then you can, of course, put these on a number line so you kind of get a sense of where the different ones are. We throw a 0 there, we go 1, 2, 3, 4, 5, and make that a 1, 1, 2, 3, 4, 5, make that a 2. And we'll go this way, 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5, maybe 3. Okay. Is there anyone who would like to come up to the board and tell me where -5 halves would be? Anyone come up and show me where -5 is?
I think so.
Okay, how about this? I'm going to start here, and I'm going to move, I'll start at 0, which way should I go? Left. Okay, tell me when to stop.
Stop right there.
No, you got shot down. Keep going. Right here. Okay, so -5 halves is obviously about -2.5, so right in the middle. Okay. All right, what about square root of 2? Which way do I go to start? To the right, because it's positive?
Positive.
Listen, I said stop at the beginning.
Okay, now time out. Square root of 2 cannot be bigger than 2. Okay? Is it bigger than 1?
Yes.
Yes, because 1 times 1 is only 1. Okay, so that's not big enough. 2 times 2 is 4, so that's too big. So it's going to be somewhere between here. Anybody know kind of the approximation is actually on the last slide. 1.4-ish, I think it was over here. 1.414. Okay. So that's going to be right around here somewhere. Okay, now here's a good question. Could I really put that point exactly where the square root of 2 is?
If you make it big enough.
You could, I could cover, right. But the square root of 2 is what kind of number? Irrational number, and so it doesn't actually have a spot on the number line. I could just keep zooming in and zooming in and zooming in and get closer and closer and closer to that. Okay, and then 2.6 repeating. I'm going to go this way and I'm going to stop at right about here. Okay, that's 2.6, so it's going to be right in there. All right? Okay, we won't make you do that. All right, how about this one? Square root of 17 and 3.8. ¿Quién es más macho? Which is bigger?
3.8.
Square root of 17 or 3.8? 3.8. I want to see the square root of 17s.
Oh, wait, yeah.
And I want to see the 3.8s. Okay, so we're all in agreement? 3.8? Okay, how do you know? Someone raise your hand and explain to me how you know. Yes.
4 times 4 is 16, and that's still smaller than 17.
Nice. Okay, so you guys follow that? 4 times 4 is 16, so we want the square root of 17. It's going to be slightly bigger than 4. We don't know exactly what it is, but we know it will be larger than the square root of 17. Okay? All right, so good strategy then, what Garrett was doing is just find the nearest number that you know the square root of and compare it to the one they're asking about. All right? Okay, again, just turn to your elbow partner. We don't need to write this down. We want to compare the square root of 26 and 6.25. Go talk amongst yourselves. Okay, show me the square root of 26 is bigger.
Stretching up in here.
Okay, yep, just stretching here. Okay, someone show me the 6.25 is bigger. Okay. You explain yourself. Defend your answer. Go ahead. No, maybe you guys are all wrong. It's happening. What made you think that the square, I don't mean to put you on the spot, but why do you think the square root of 26 is?
Like 4 point something.
Okay, and then this is?
Lot.
So which one's bigger, the 4 point something or the 6? Okay, so I think you're actually agreeing with everybody that this is, you just had it. Okay? All right, yeah, so this is going to be bigger than that. All right. All right, that's what I don't care about. The properties, okay, we better just touch on it real quick. All right, so if you want to jot this down in your notes, I suppose. As you are copying this down, if you want to, I will read this to you. There's some different properties that real numbers exhibit, some of them. One is called the closure property, and that is that if you add two of them together, you still stay in the same set of numbers. So in other words, if you start with A and B and they're both real numbers, every time you add A and B together, you still get a real number, okay? And every time you multiply A and B together, you still will get a real number, okay? And that doesn't always hold true, but if it does, then that's called closure. Then you remember commutative, of course, from like 8th grade. That's where if you do the thing in the opposite order, it still comes out the same. 3 plus 2, 2 plus 3, same difference. 2 times 3, 3 times 2, no big deal. What are a couple of operations that do not work for the commutative property?
Division.
Division, because if you go 10 divided by 2, that's going to be very different than 2 divided by 10. And then, of course, subtraction. Okay, so don't take that for granted. Associative property is just how you are grouping them together. So you could add the A and the B first and then add the C, or if for some reason it was easier, are there any golfers in here? Anybody on my golf team? Okay, when kids come in with their scorecards and they've got 4s and 5s and 6s and 7s and 3s and they get out their cell phones to add these up, I'm not even kidding. I'm like, okay, no, don't do that. I can add it up for you. I just go through and I grab pairs of 10. So 6 and a 4 makes a 10, a couple 5s makes a 10. And it doesn't matter if I add their score on the first hole and the fourth hole together, I'll still get the same answers if I just added them up in order. So that's what the associative property is about. You can kind of group them how you want. Identity means you do a little thing to it and you end up with the identical answer. And then the inverse is a little different depending on if you're doing addition or multiplication. In the addition world, the inverse is you add them together and you get 0. In the multiplication world, you multiply them together and you get 1. And then everybody's favorite, the most important property, the distributive property. So if I were to multiply A, I have to, by B plus C, I have to multiply by both of these things in here. I can't just do one of them. Anybody in here ever have Mr. Helby, or are we done with he was going? You have Mr. No?
No,
Okay. So you guys, you know who that is a little bit? Like,
I've heard before.
He used to talk about like the distributive property. You're rescuing someone from a burning building. You have to go in and get both of the people. You can't
That's
just.
okay.
Okay, that's what's parking too. Okay, yeah. So you got to get both of those things. All right. Okay, so I'm going to be bad teacher. I'm going to change the slide, even though some of you are still copying this down. Remember, it is in your book on page 14 if you want to finish that. But I want to go ahead and finish this lesson. All right, what property does this illustrate of the ones that we just looked at? And multiply two things together, we got an answer of 1. Which one of these things is demonstrating that?
I know.
Multiplicative inverse, because we're multiplying. So that is going to be the inverse property. Because negative 2/3 and negative 3/2 are inverses of each other, right? You flip the fraction, find the inverse, okay? All right, how about this guy here? 3 times 4 times 5, or I could go 4 times 3 times 5. That's not the associative property you would think it was because of the parentheses, so you're sort of trained to do that. But what I did here is I changed the order of the multiplication. And so when I changed the order of the way that I'm doing that, that's which one? Commutative property. So I'm not sure that I can actually spell it correctly. Commutative property. Okay? You remember this, right, from 8th grade, not going through these things? Okay. All right, so here is...
Great.
This is my class.
Just hang on. Okay. I recorded, did you see that?
What is that thing, by the way? The blue light? Blue lights?
That horse.
That's a clock.
Oh, I get you.